Okay, so let's move on to the next section of Chapter 1, and this is the section on units. Okay, units, we all have experienced units before. We all know what units are. Units are a standard measurement, something like 1 meter, 1 second. But let's talk a little bit more about why we defined units to be the way they are, and why do we use certain units in this class and not others. Globally, scientists and engineers have all agreed to use the same unit definitions. And so we call these SI units. This is from the International System of Units, so that doesn't seem like SI, right? But in French, it's Système International, so that's where the SI comes from, right? Also known as the metric system, but typically you hear it referred to as the SI units, okay? And so this is something we've all agreed on. So for example, the kilogram is defined relative to this one metallic cylinder which is located in a vault in Paris, right? That is what a kilogram is. It is that piece of metal, and that's what we've all decided is a kilogram. And I'm going to talk a little bit more later about how that definition may change in the coming years. So ask yourself, what would happen if we didn't have these standard units? And in fact, I'll show you some examples of what happens when people mess up on their units. And also think to yourself, what are some SI units that you've used in your life? And I'll talk about that more on the next slide. So okay, SI units, or Système International, these are the standards used by scientists and engineers, and SI units fall into two general categories. There's what we call fundamental units. These are defined relative to actual measured quantities, like that kilogram we saw in the previous slide. And then there are derived units. These are defined relative to the fundamental units. So there's actually only 7 fundamental units in SI units: the meter, the kilogram, the second, the ampere, the Kelvin, the mole, and the candela. Okay, that's the only fundamental units we have. And in this class, we're really only going to use 3 of those, right? The meter, the kilogram, and the second. You'll use the rest in future physics classes. Everything else is derived, right? What we mean by derived is that they're based on these fundamental units. So for example, the unit of energy is something called the joule, right? Or just the symbol capital J. But what the joule is it's equivalent to a kilogram meter squared per second squared, right? So it's based on these fundamental units. So the joule is a derived unit that's based on these fundamental units, okay? The fundamental units, again, are defined based on real things you can measure. Right? The second is defined using atomic clocks. Right? There's a cesium atom which oscillates at a certain rate, and so you build a fancy atomic clock, and you can measure that, and that's how the second is defined. As we talked about, the kilogram is defined using the standard, this platinum iridium alloy cylinder, which is in this vault in Paris. Right? And then the meter is defined based on light. So light travels a certain distance in a given amount of time, and that's how we define the meter. So that's the distance light travels in 1 over this big number of a second, this big fraction of a second. Okay, that's how we define a meter. Okay, a little bit more about fundamental units. Just to let you know, the definitions of our units have changed with time, and so you have to be ready for that to happen in your career, right? The definition of a kilogram may change during your career, right? And hopefully, as time goes on, the uncertainty that comes with how we define these things will decrease. And just as an example of this, the meter has changed in its definition with time, okay? In the 1700s, the meter was defined to be 1/10,000,000th of the distance between the North Pole and the equator. Right, that's how the meter was defined. You can imagine that's not the most accurate definition in the world. So in the 1800s, instead, they decided to use just a standard metal bar to define what a meter is. But again, that works, but a metal bar changes in size, right? As temperature changes, metal is going to expand or contract, right? So a metal bar is not the best way to define a meter. In the 1920s, we started defining the meter based on the wavelengths of light. And finally, it wasn't that long ago, 1983, the meter was defined using the speed of light. Right? So the definition of a meter has changed with time. Also, the kilogram actually has this interesting thing going on. The kilogram that I told you about that's sitting in that vault in Paris has a weight loss problem. That kilogram has been actually losing a few atoms every year, and that metal cylinder is actually changing in weight, and so that's not a good thing. So there's an ongoing effort to use kind of a more complicated but a more accurate method to define the kilogram, and that's ongoing, and you can read more about that in these links below. Okay, what about derived units? Derived units are units defined with respect to the fundamental units. Some of them have new names, and some of them do not. Right. So, for example, if I measure the area of a rectangle as length times width, or multiply the two sides of the rectangle, that area is just meters squared. Right. It doesn't have its own name. Similarly, for speed, the SI unit for speed or for velocity is meters per second. Right. It doesn't have its own name. It's just meters per second. Where other things we're going to do in this class have their own name. For example, the unit of force, when I push on an object, we're going to measure that in the Newton, or a capital N. But a Newton is defined as a kilogram times meters per second squared. So this derived unit is based on these fundamental units. Okay, if you forget this, if you forget what the definition of a Newton is, you're always going to be able to figure it out. Right? Because if you know our equations for force, which you'll have on your equation sheet in this class, for example, force is equal to mass times acceleration, well, if this is a Newton, the other side of the equation also has to be in newtons, but I know mass is kilograms, and I know acceleration is meters per second squared, so I can always figure out what a Newton is using this formula. Another derived unit that has its own name is the Pascal. This is a unit of pressure, right? The Pascal is just the SI unit for pressure. There's other units for pressure maybe you've used in your life, something like a PSI or a millimeters of mercury, or there's all sorts of pressure units. But the SI unit is a Pascal. It's defined to be newtons per meter squared. Right? We can always figure out what that means because pressure is force over area. Right? Force is measured in newtons. Area is measured in meters squared, so we can always figure out what a Pascal is. And I can always figure out what a Newton is, so I can figure out that a Pascal is a kilogram per meter per second squared. Right? Again, that's the derived unit based on fundamental units. And finally, energy, our unit again is a joule. If I know the equation for kinetic energy, I can always figure out what a joule is. Kinetic energy is 1/2 mass times velocity squared. Mass is kilograms. Velocity is meters per second. I square that whole quantity, so I know that a joule must be a kilogram meter squared per second squared. Right? And I can always figure out what that is. And on a test or in a homework, you can write answer. If I ask you what is the energy, you could report your answer in joules, or you could report your answer in kilogram meter squared per second squared. Either is okay. Okay. The joule is just a way of doing shorthand. It's easier to write down a J than all of these symbols. Okay. A quick side note, there's other conventions within the global SI units. Our textbook uses the convention of using meters, kilograms, and seconds. Right? This is what we use when defining derived units. For example, the Newton was defined again using kilograms, meters, and seconds. So why did we choose to define the Newton in terms of the kilogram and not in terms of the gram? Well, we just made that choice, that all of the units in this class will be defined based on meters, kilograms, and seconds. And for that reason, this is called the MKS Convention, meter, kilogram, second. If you look at an old textbook, maybe a 50-year-old textbook, you may see people using an alternative SI unit convention, which is called CGS, where units are defined using things like centimeters, grams, and seconds. Right? And so an energy in this textbook could be measured in ergs instead of joules, right? Because that's defined using centimeters, grams, and seconds. It's still an SI unit, but it's just a different convention. But just to let you know, MKS is a modern convention, so this is what we should use in this class. So in general, when you're solving problems, before you even start trying to solve the problem, convert any numbers they give to you into MKS SI units. Okay, and you should report your answer using SI units using the convention of meters, kilograms, and seconds. Okay, and finally here, my last quick thing about units is, of course, there are unit prefixes. So there's grams, but there's also kilograms, which is 1,000 grams, and megagrams, and gigagrams, and centigrams. And just make sure you understand these prefixes. You can always look them up. I found this table on Wikipedia. But generally, no matter what they give to you in a problem, whether it be millimeters or whatever they give to you, you always want to report your answer in meters, kilograms, and seconds. If you need to use scientific notation to do that, you should. Okay, so make sure you understand your prefixes, and this table is here for you as a reference. Just as a little aside, a little break, let's tell some fun stories. What happens when you don't have good units? So here's my first fun example. In 1628, Sweden built this new ship. It's called the Vasa. And it turns out this ship sank on its maiden voyage. What happened? Well, it turns out that they used two different definitions of a foot when they were building this ship. The carpenters on one side of the ship used a different definition than the carpenters on the other side of the ship. Right? So it ended up the ship had walls that were much thicker on one side than the other, and so when it went out to sea, it just tipped over and sank. Right? That's our first example of why we need to all agree on good units. A more modern example, in 1999, the space probe, the Mars Climate Orbiter, launched from the Earth, flew all the way to Mars, and then when it got there, instead of orbiting Mars, it just crashed right into Mars. Right? What happened? Well, this was another unit mistake. NASA uses SI units, as everybody should. All right? This is in an SI unit, the unit of force is a Newton. But one of the contractors who wrote the trajectory software for this satellite used what are called imperial units, where the unit of force is a pound. Right? And so the conversion was off, and calculations were off for that reason. Another more recent example is in 2003, some folks were building a bridge over a river between Germany and Switzerland. And workers began building the bridge from one side, and workers on the other side of the shore also began building the bridge, and they were planning to meet in the middle. And when they met in the middle, one side was half a meter higher than the other. Right? How could that have happened? It turns out Germany and Switzerland have different definitions of what sea level is. Germany defines sea level to be based on the North Sea, while Switzerland defines it based on the Mediterranean Sea. Right? So not only do we have to agree on units, but we have to agree on things like sea level and what are we calling zero, what are we calling our standards here. And then my final example is the 1983 jet that had to emergency land because it ran out of fuel. How did it run out of fuel? Well, the pilots were using something called a float stick to measure how much fuel was left in the tank before they lifted off, and they used the wrong conversion factor. They didn't convert their units properly, and therefore they added 5,000 liters of fuel instead of 20,000. Right, so that's another example of a unit mistake, and this time it was a unit conversion problem, which is our next topic. Okay, so unit conversion. So remember, the goal here is to convert everything into MKS derived units, meters, kilograms, and seconds. We want everything in SI, meters, kilograms, and seconds. And the rule, the way we do this, is to convert to standard units. What we want to do is form a ratio of the same physical quantity in two different units and use it as a multiplier. Right? So if I said convert 3 minutes into 3 minutes to seconds, first we need to look up, or we know that 1 minute is equal to 60 seconds. Right? That's an equivalent statement. 1 minute is equal to 60 seconds. So how do we do this conversion? Well, we want to multiply 3 minutes by this conversion factor. So how do we decide, is it 60 over 1 or 1 over 60? We have to decide that we want the minutes to cancel out so that we end up with just the seconds in our answer. Right? And then we can check our answer at the end. Does our answer make sense? I definitely know there are more seconds than there are minutes, so 3 minutes, I must get a bigger number at the end. Right? 3 minutes is equivalent to 180 seconds. Right? Another way to check your answer is if your units look wrong at the end. Say I had chosen to multiply 3 minutes by 1 minute over 60 seconds instead of 60 seconds over 1 minute. Then I would have gotten 1 over 20, and my units wouldn't have canceled. I would have gotten minutes squared in my numerator and seconds in my denominator. So I wouldn't have ended up with seconds in my answer. So you want to develop some physics intuition to make sure that your answers make sense in this class, and you also want to just write down your units when you're doing these conversions and when you're solving problems, and at the end of the problem you should end up with the units that you're looking for whatever quantity you're trying to solve for. Okay? And we'll do some more examples of unit conversion in some future videos, but quickly I wanted to make sure we talk about converting units of area and volume, because this is a really common mistake. People make mistakes when converting area and volume all the time. So say I asked you convert 1 cubic meter into cubic centimeters. Okay. So first, what do we know? We know that 1 meter is equivalent to 100 centimeters. What do we do next? Well, we turn this into a ratio. I'm going to divide both sides of this equation by 1 meter. Right? 1 meter divided by 1 meter is just 1, where 100 centimeters divided by 1 meter is just, I write that out like that. Okay? And now this is equal to 1. Right? I can multiply anything by 1 and not change it. Right? So I can take 1 cubic meter and multiply it by 1, multiply it by this ratio, 100 centimeters over 1 meter. But I can't just use that ratio, right? Because I need my units to cancel out. I need this cubic meter to cancel with something. So I need to cube this ratio, right? So that I have meters cubed in my denominator, and these cancel out. And so what I end up with is my answer in cubic centimeters, right? Centimeters cubed. And look, I had to cube my conversion factor. I ended up with 100 cubed, so there's 1,000,000 cubic centimeters in 1 cubic meter. All right, so that is a very common mistake, so make sure you do that. And if you make this mistake, you should be able to realize it for multiple reasons, right? First, if I forgot to cube my conversion factor, I would have ended up with 100, but my units wouldn't have canceled out, so my units would be real strange. It'd be meters squared times centimeters. It doesn't really make any sense. And secondly, if you got the answer of 100, you can think about physically how many cubic centimeters could there be in a cubic meter. A cubic centimeter is tiny. It's the size of a sugar cube. A cubic meter is huge. Right? So you can definitely fit more than 100 cubic centimeters in a cubic meter. In fact, you can fit 1,000,000 cubic centimeters in a cubic meter. So make sure you go through the conversion factor fully and check your results. One other quick statement I want to make about units is when you're solving problems in this class, you want to make sure that your answers are dimensionally consistent. Right? What does that mean? When you're adding terms, first off, make sure that you're adding or subtracting things that have the same units. Right? It doesn't make sense to say 3 meters plus 3 seconds. Right? You can't add lengths plus time. Secondly, check your units. If I want to figure out something like I'm traveling at 2 meters per second for 5 seconds, how far have I traveled? Distance is velocity times time. Right? I could plug in for velocity, that's 2 meters per second, plug in for time, that's 5 seconds, check. My seconds cancel. I ended up with my right side of this equation has meters. I end up with the answer 10 meters, which is a unit of distance. Right? So just make sure you write out all your numbers, write out all your units, and at the end of your equation, make sure you get whatever quantity you're looking for. I'm looking for a distance, I better get an answer in meters. So that's a way to check your answer. Okay. As an example of this, why don't we quickly look at this cylinder and say I incorrectly told you that the volume of a cylinder was given by this equation. It's pi times the radius cubed times the height of the cylinder. How would you immediately know that I'm wrong? Right? So think about that for a second. Right? You would know that I was wrong because the units don't work. Right? Volume has units of meters cubed, but this equation has units of meters to the fourth. Right? Radius is measured in meters. Meters cubed times height, which is also measured in meters, gives me something of meters to the fourth. So this equation cannot be right. Right? So it's a way of just making sure you're doing the right thing is always considering your units. Okay. So in the next video, we'll talk about sig figs.